Right, I'm going to show you how these retro reflectors work. So this little box here is mirror, 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 and they're at 90 degrees to each other. Now I don't have a protractor, so I'm going to improvise with a piece of acetate film. So it says, show how light entering the retroreflector from two different angles results in reflected light that is parallel to the incidence ray. So let's take this bottom one first. This is our incidence ray, and this is the angle of incidence. It's measured to the normal, this dotted line at 90 degrees, so this is 90 degrees. That angle is our angle of incidence, and this is the incident ray. So, because I lack a protractor, I'm going to have to make a little kind of drawing on here. So I'll put a little line on there to match up with the bottom of the mirror. Now I'm just going to put my line on my incident ray on, and then I can just cleverly turn it over to get it where it would be, and therefore I can line that back up on there, put that back on there, get my ruler, put a little point where it meets, and then I can line that to it, and therefore I've got those angles are the same. That angle I'll call X is the same as angle Y. Okay, so and that's our reflected ray that then hits this mirror again. So I can rub that out a bit. It's not permanent ink on my sheet. So first thing I need to do now is to draw a normal. So I tend to use the line there to just make sure that that's 90 degrees. Again, I'm doing this without a protractor. That should work. So again, there's my mirror line, and draw my line that hits it. Again, it would be so much easier with a protractor. I don't believe I've come home without a protractor. Again, it's not something I use often, I must admit. And put that there. Get my ruler on that blue line. I'm way over here now. Put a line there and draw my line to it. I've done it. You can see how my first line, boing, boing, this line here is parallel to this line. Okay, so if the light source is here, it goes back towards the light source. You know, this little retroreflector might be like 1 millimeter. You know, this distance here might be 1 millimeter. So it comes back within 1 millimeter of the thing that shone it. And often clothing that contains this has millions of these little reflectors in it, and therefore it comes back to the same point. I can do the same for the other one as well. Just wipe my thing off again. It's a bit messy, but doesn't matter. Just clean it a bit more. Upside down. There it was. Right, so there's my line. I'll do this quickly now without narrating. Turn it over. I've no space to draw it. Use my board. I'll dot that. Looks about right. Again, I'm doing this a bit faster now, so again, it's very easy to lose accuracy. And if you lose a bit of accuracy, then it can be disastrous. Pop on my normal line again. However, that's a word we need to know is normal, and then so a quick fresh one. So that's that line. Oh, smudged it, never mind. That's that line. Flip it over. Pop it on. It's coming to there, isn't it? Get my ruler, just knock the paper. There we go. My first line is parallel to the second one. So no matter what angle I send this light in, it always comes back parallel to the incident ray. So again, this is coming in at a narrow angle, and it boings, boings, boing. If I came in at 90 degrees, it'll just boing back. So wherever you send the light, it comes back to the source. Whereas if you just had a single mirror, oops, if I just, on my bike, instead of having a reflector, if I just had a mirror on the back of my bike, then when the light hits it, it'll bounce off over here, and therefore you wouldn't see the reflector. If these were my car headlamps, I'd just send the light somewhere else. Again, that's badly drawn. Also, while I've got this, you know, mirrors are made of glass, a very flat surface with silver behind them. Not silver as in real silver, but you know, like a silver material, like aluminium, and therefore light can't get through. And a bird just flew into the window. So light can't get through, and it's smooth, so it reflects back in a known way. If you know, I shine light onto paper, well, paper is rough, so there's lots of little angles. So light coming here can strike there, and it would bounce straight back. But another light ray that hits there, well, that's gonna go over here. Another light ray that comes here, that's going to go there. You get a scattering of light from all different angles. So yeah, so when we do about reflection, we're dealing with these very flat surfaces, yeah, that glass is. But yeah, most surfaces aren't, and therefore I can shine a light on a white wall, and it bounces back in loads of places. Okay. While I've got you as well, you're going to be doing some work on mixing light. I just grabbed a piece of paper here. In your books, it's worth knowing the mixing of light. So it's best shown by just draw 3 circles like that, and then I want you to tell me what the colours are in terms of your notes and remembering it. In terms of light, you know, I've got red light and blue light. Well, when I mix red and blue light, I get a magenta light, and therefore in your books you might want to put red or equals red, M equals magenta. So like a little diagram like this in your books with a key, so you know that if you mix red and blue light in equal amounts, you make the colour magenta. So that might just help you with the task that I will set you after. Okay.